Welcome back, everyone. In this video, I'll be continuing the work section. Now, as we talked about in the last video, we really built up what we're doing here. In order to find the work done by something that has force that is changing, what we have to do is we have to integrate the force function. All right, so let's go ahead and read this setup. So Hooke's law applies to the springs that are stretched beyond their natural length, which is one of the things I described in the previous section. It says Hooke's law states that the force required to maintain a spring stretched x units beyond, so that's the key word, is beyond its natural length, which is called the equilibrium, is given by the formula f of x equals k times x, where k is called the spring constant. Now, one thing is that every spring has a different spring constant, so you can't say k is always 4, or k is always pi, or something like that. You have to figure it out in each problem. All right, so let's go ahead and see what we've got here. This problem says, if the work required to stretch a spring 1 meter beyond its natural length is 5 joules, how much work is needed to stretch it 50 centimeters beyond its natural length? Okay. Now, in terms of work, all we have to do is integrate the force function. But the problem is force function for this, since it's the spring, it's f of x equals k times x. So we don't have x. How are we going to figure this out? Well, when you're given the work in the first problem, so it says the work required to stretch a spring 1 meter beyond its natural length is 5 joules. It's telling you how to solve for k. Why is it telling us how to solve for k? Well, the idea is, if you read this closely, what it's saying is that, let's say we have a spring with our mass attached to the end. It doesn't really have to have a mass attached, but it's just easier to think about grabbing a mass than grabbing the end of a string. And we have our wall here. So maybe this is its equilibrium length. Well, what this problem is saying is that if we stretch it out 1 meter farther, we don't know how far its equilibrium length is. It could be 1 meter, it could be 100 meters. It's not important. What it's saying is that this requires no energy because it's its natural state. So if it goes 1 meter further, so this is just going to be the same string drawn right next to it just to really talk about what we're comparing here. It says if we go 1 meter beyond, so this is 1 meter, then the work required to do this is 5 joules. All right, well, how is that going to help us? Well, what is work? Work, by definition, is the integral from a to b of f of x dx. Now, we know in general our force function is k times x for this. But what is a and b? Well, think about your equilibrium position being x equals 0. So this isn't really here, but this might help a lot, is if you think about this being x equals 0, the equilibrium, how far are you stretching it? Well, we're stretching it 1 meter. And what might help is realizing that these are actually bounds on our integral. So this is x equals 1, where we want to stretch. So this is saying if I stretch from x equals 0 to x equals 1, the work done is 5 joules. So that means I should integrate kx from 0 to 1, and this is representing the work done, and we are told that the work equals 5. And that gives us an equation that allows us to solve for k. So we can solve this for k. And that's necessary to do the next part. So we can't really do anything about the second part yet and to actually answer the question until we realize that we are having the ability to solve for k based on what it's telling us. Well, let's just go ahead and solve this. Now, it might look a little intimidating at first, even though the integral itself doesn't look too bad because we haven't solved something like this. So we got 0 to 1. I'll start with the kx dx. We'll just remember this equals 5. But if you want to solve for k here, what you want to do is realize that k is a constant. We don't know what it is, but it's a number. So if we bring it outside, we can do that just fine based on our integration rules. And we have to integrate 0 to 1 of x dx. Now just let k be along for the ride. It's not going to do anything for a while. We want to go ahead and integrate x. Well, x is just x squared over 2. And we want to integrate from 0 to 1. Well, let's keep going. So we still have the k here. Go ahead and rewrite it again. And if you want, you can bring the 2 under the k, just to make it a little easier to plug in x for x squared. All right, so we got k over 2, and then we want to plug in x equals 1, so we get 1 squared minus x equals 0, 0 squared. And 1 squared minus 0 squared is just 1. So we get k over 2 when we integrate this thing. Well, the thing is, now it's supposed to equal 5, because this is exactly what we started with right here. We just went through and kind of solved it in a way. And we got that it equals k over 2, but it's also supposed to equal 5. So we can go ahead and solve this for k. And when we do that, we can just multiply each side by 2, and we get k equals 10. Now, why is solving for k so helpful? Well, now that we know the spring constant, what we can do is we can go ahead and figure out the work based on our own problem. So we want to find not the, grab this here. We don't want to know how much work is needed to stretch it 1 meter, because that is the answer of 5. We just want 50 centimeters. Now do be careful here that 50 centimeters is 1/2 of a meter, because there's 100 centimeters in a meter, and you must use the same units. Since we used meters before, you must use meters. This isn't one of those things where you can just say, oh, it'll be 50, and then at the end I'll divide by 100. You have to use meters from the beginning. Well, how would you set up this problem? In order to find the work for our answer here, we want to set up an integral again, because work is computed by integrating the force function. But the force function here, it's k of x, but we figured out k is 10. So we got 10x dx. And we only want to stretch it 1/2 a meter beyond its natural length. So we want to integrate from 0 to 0.5, or 1/2. Whichever one you want to write. You can write 0.5 or 1/2. It's the same thing. But the idea here is, if you wanted to figure out how much work is needed to stretch it 2 meters beyond its natural length, you would integrate 0 to 2. If you wanted to integrate or figure out how much it's needed to stretch just 1 centimeter beyond its natural length, it would be the integral from 0 to 1 over 100. Okay, so after you figure out k, you can do any number here. Just make sure you're using meters. All right, so let's go ahead and integrate this. You can leave the 10 there, bring it out. I'll just leave it there because with a 10, we're more comfortable with this. Integrate x, you get x squared over 2. And then that's from 0 to 0.5. If you want, you can simplify the 10 over 2 to be 5 first. And then what we can do at this point is we can plug in the 0.5 and the 0. We got 5 times 0.5 squared minus 0 squared. And 0.5 squared, that's 0.25. We got 5 times 0.25 minus 0, 0.25. And that simplifies to 1.25. Now remember, our units for work, they'll be the same as the work units we were already given, but because everything's in meters and joules and everything else, it's J for joules. Okay. Now, kind of a much more complicated example, but remember, in order to ever work with a spring, and you want to find the work done using a spring of some sorts, you have k times x, and you must figure out k first. And you're going to be told how to do it, at least based on something in the problem. Okay. Now the next one is probably even a little more challenging, maybe the most challenging problem in the entire course, or one of them at least. We have a tank that's full of water. So this thing is full of water. I just didn't want to draw in blue and kind of convolute the picture a little bit. So we have a tank that is full of water, and you want to find the work W required to pump the water out of the spout. So there's this spout up here that's 4 meters tall, and basically this pool of water, whatever you want to call it, a tank, has a triangle as its shape, sort of like a cross-section shape, and it's a triangular prism. So it's 12 meters long. The height of the triangle is 4 meters, and the width of the triangle is also 4 meters, or the base if you like to use the word base. All right, now in order to do this, we want to use gravity is 9.8 meters per second squared, and we want to use that the density of water is 1,000 kilograms per meters cubed. Now, the reason we need both of these is that, remember, force is mass times gravity, right? And the reason why we're thinking about gravity is what it's trying to do is we're trying to pump the water out. So the water's sitting in the tank and we want to pump it out of the spout. So it's got to fight gravity to come out. Right? That means that we're going to use forces mass times gravity. Right? Now, as far as the gravity goes, G, we already know that this is going to be 9.8 meters per second squared. And for the purposes of us, we're mainly just concerned with using the number 9.8. Now, the mass is what's a little more complicated, because the easiest thing to do is probably take this thing and say, okay, if you understand density of water, you can figure out the volume of this object and then multiply it by the density of the water, and then just think, oh, I have that much weight or that much mass, and if I multiply it by gravity, I get the total amount of force. Well, the problem is the force is changing based on your depth. So what I mean by this is that we have to get the water to come out at this height, which is 8 meters above the top. It needs to come out way up here. Well, what happens is, let's pretend I'm just going to take a little slab here, like we do in a lot of problems, and take a horizontal slab like this. So it's the same thing on this side over here. So this gives us a really, really tiny rectangular prism. Well, the weight here and the distance it has to travel is much different than the one up here. So the one up here, think about the water sitting on the top. It's got a different volume as far as the rectangular prism goes, because the base would be wider, and it also has less of a distance to travel because it only needs to go up to 4 meters. Something down here, let's say, this is 8 meters long, the bottom would have to travel 4 meters, the top would have to travel somewhere in the middle, maybe 6, has to travel 6 meters. So what's happening is that the distance traveled is changing as well. And that's going to be a very important thing, is that, one of the parts about the work is the distance, but it's not so much inside the problem itself, it's when we set up the integral. Now, with all this in mind, what we want to do is go ahead and start to set up sort of an axis just to represent everything. Because we have different distances, different heights, basically, something on the bottom has to travel 8 meters while something at the top only has to travel 4 meters. We really need a way to represent this. So what I typically do, I'm just going to actually draw the front triangle, because what's happening is that everything is the same behind it. It's just 12 meters long. So I'm just going to draw the front triangle and really talk about everything based on that. All right, and we also have this spout here. All right, well, based on the picture here, this is 4 meters tall, and then the spout's also 4 meters tall, and this is also 4 meters wide. Now, the fact that these are all the same number is not very important to the problem at all. That's just a coincidence. Well, what a lot of people like to do is go ahead and say, okay, I'm just going to call where it's exiting the y=0 mark. I like to use the letter y because everything's being done vertically. Some people still like to use the letter x, which is fine, but I'm going to use the letter y. So this is my y=0 mark, and y is just going to represent the depth. So I'll draw in a couple more spots here just to explain a little better. So at this point here, where the spout ends would be y equals 4. And then at the bottom, we're 4 more farther down, so this is y equals 8. So this is just y is measuring the depth. Right, so we'll keep that in mind. Now, what is the distance each slice has to travel? So I'm going to take the same little rectangle and draw it on here. And the distance it has to travel, well, that's from 0 from its depth of y. So it has to go from y to 0. Well, that's just y. Okay, so the distance traveled, actually, let's use y0 to just represent a different number. The different distance it has to travel is y equals y0 minus 0. So it has to go, let's say this is 6, it has to go from 6 to 0, which is 6. That's y0. And then the main thing is that what is the area of this little rectangle? Because when we get the area, we can multiply it by 12 to get the volume. So we also need, what is the area of this rectangle? All right, and this can be probably the most confusing part. And it's because of the way the problem is set up. It's really up to you how you set up your axes. What I would go ahead and recommend you do next is that you actually draw on an x-axis, or sorry, a vertical axis to reference everything. I'm going to go ahead and do that. I'll use, let me actually use blue here since blue is not in the picture yet. I'm going to draw it right down the middle. So this is like my vertical axis. You can call it x if you want. It's kind of backwards because we're used to x being the horizontal and y being the vertical axis, but no big deal. I'm just going to call it x. Actually, this is still y. What am I talking about? This is y, y-axis. It really just depends where you draw on the x-axis. That's really what I should be saying. And I like to put it at the bottom of my pictures. The reason is because if you put it at the bottom here, so let's say the x-axis is right here. Okay, then what's happening, just to kind of view everything, is that the sides of your triangle here are lines, and you can find the equation of the line based on the width here and the height and everything else. So let's go ahead and look at this. Now that we've got our coordinates set up, what we can do is we can figure out the equation of just the line, let's say in the first quadrant right here. And that will allow us to get a number, or not a number, but a representation for the x value. And since the x value is going to be, since this exactly cuts the triangle in half, we can just double the x value, and that'll give us the width of this rectangle. And that's really what we need. After we get the width here, we'll actually have everything we need to be able to plug in and solve for everything. Right. Now, probably the most confusing thing about this picture is that because y is representing the depth, y is actually going up as we move down. But if you just use your normal coordinates of everything, just use the x and y appropriately, you'll actually be able to find this just the same. So at this point here, since it's the y-axis, this is where x is 0, and then our y value is 8. And at this point here, the x value, well, you can figure it out because the width here is 4, that it's going to be 2 and 2 on each side. So the x value here is 2, and the y value is 4. So what we want to do is we want to figure out the equation of this line. We have y equals, mx plus b, and m is the slope of the line here between these 2 points. So it's y2, let's just say that's 4, minus y1, which is 8, over x2. Well, I use this as y2, so x2 is going to be 2, minus x1, which is going to be 0. And then this is negative 4 over 2, which is negative 2. Now, if that seems a little weird, it's because, once again, that the y is going down as we move up, so the slope being negative seems kind of weird. But just know it's because everything's backwards. If you had used y equals 0 to be down here, and you had increased it, then your slope would be positive 2. But there would also be a different formula for the distance traveled and everything else. All right, so we got that. Now we can plug it in. We have y equals negative 2x plus b. Well, we can also get b fairly easily because b is just representing the y-intercept, and at x equals 0, the y-intercept is 8. So b is actually just 8, and you could plug it in just to check. We get y equals negative 2x plus 8. So just remember that the y-intercept is always the y value when x is 0, and we already have it here, so we don't really need to solve for anything. But what we need to figure out the width is we need x. Y doesn't really help us because y is telling us how high up we are. X is telling us how far over we are. So we need to solve this for x, and that will give us half of the width. And if we multiply it by 2, then we'll get the other half, which will give us the total width. All right, so let's go ahead and solve this for x. You can add the 8, subtract the 8 to each side. We get y minus 8 equals negative 2x. And then we can divide by the negative 2. And when we do that, I'm just going to leave it like this for the moment. We have x equals y minus 8 over negative 2. But we really are interested in the width, like I've mentioned a couple times now. So I'm going to multiply this by 2. And the width of that rectangle here is equal to 2x. Well, if we multiply what we got here, x by 2, we get 2 times y minus 8 over negative 2. The 2's cancel. So we've got y minus 8 over negative 1. And all negative 1 does is it divides everything by negative. So we got negative y plus 8. And if you prefer, you can write it as 8 minus y. It's totally up to you. All right, so that is the width of the rectangle that we've drawn here in red, because it's the left and the right extension. The main thing about the height is that it's just delta y. It's just some small thing, small change in y, because we're going to have infinitely many of these rectangles. So the height of the rectangle is just delta y, some small change in y. It's the part that becomes the dy in the integral. So really, when we kind of fill out our integral, this won't necessarily be here, because the y here is what's representing the change, but its height, it becomes shrunk down because we're going to make infinitely many rectangles. All right, so why did we have to figure out, why did we have to figure out the area of this rectangle? Well, now that we know the area of this rectangle, if we multiply it by 12, it'll give us the volume of this rectangular prism. So just going back up here, now the volume of this rectangular prism is the area, which is 8 minus y times delta y, and then times 12. Right, so once again, just to repeat what we're doing here, this is the area of the rectangle. This part right here, which I drew again down here, and then 12 comes from multiplying by 12 to get the volume, because it's just a rectangular prism. And now you can simplify this, but there's not much to do here. I'll just put the 12 in front for the volume. Now, why do we need the volume? Well, we're building up being able to get the mass, and volume times density equals mass. So that's the whole point of why we're doing this, is that we are given the density, and the volume times the density. Actually, that's hard to read. Let me use a different color here. So the volume times the density equals the mass, and that's what we really need. But luckily for us, density is just a number here. It's just 1,000. So the mass m equals our formula for volume, 12 times 8 minus y times delta y times 1,000. 12 times 1,000 is 12,000. But once again, there's not really much else to do. This is our mass. This is the mass of the water at each sliver. So if you're closer to the top, like at the top here, the y value is 4, you would plug in 4. If you're at the bottom, the y value is 8, so you plug in 8. That's the idea. Right? And now finally, to get our final force, since now we have the mass, the final force is m times g. We have our entire m here, 12,000 times 8 minus y times delta y. And then this is multiplied by the 9.8. And you can simplify this because 9.8 times 12,000 equals, see what it equals here. Go ahead and grab a calculator. 12,000 times 9.8, 117,600. 117,600. So finally, the force is 117,600. And then that's just the numbers here. And then we have times 8 minus y times delta y. Now, the other thing to remember is that now that we have the force at each little section here, remember work is force times distance. And the distance d we figured out was just at the beginning. We called it y naught, but it's really y because it's the distance. So d is just y. And then what happens is when we figure out the work here, we could properly set up a Riemann sum, take the limit as n goes to infinity, blah, blah, blah. But really we just take force times distance and the delta y becomes dy. This is what becomes dy, and then work by definition is force times distance. So we have the integral. We'll have some bounds here to put in a second, but we have our force formula without the delta y because this becomes dy. We have 117,600 times 8 minus y, but don't forget the y here for the distance traveled. Right? So each little thing in here, the best way to really try to understand it is this is basically the work done at every little small rectangle, but we're adding up all the works to get the entirety. Now the last question is, what are the bounds on the integral? Well, you have to look at the y bounds here. What is y ranging between? The quick thing is that you don't want to use 0 to 8 because what's happening is the the triangle shape that we're forcing the water out of, it only ranges from y equals 4 to y equals 8. So we integrate it from 4 to 8. If you do that backwards from 8 to 4, because you think, okay, this is at the bottom, then this is at the top, then what happens is you'll get negative work and you can just adjust it by its sign. Right? But you can go ahead and now integrate this. We can bring out this 117,600. We're integrating from 4 to 8. What's left inside is 8 minus y times y, which is 8y minus y squared. And we can integrate this 117,600 out front. 8y's integral is 4y squared minus, and then y squared is y cubed over 3 from 4 to 8. Unfortunately, it's not 0 and 1 like it is very often, so we have to plug in both of these. We have 4 times 8 squared minus 8 cubed over 3 minus, and then plug in 4. You have 4 times 4 squared minus 4 cubed over 3. And at this point, we've done so much work that it's probably best, especially just to be careful and go ahead and just use a calculator. We got 117,600. And then I'll use double parentheses. Once for the outside, the first inside, we have 4 times 8 squared minus 8 minus 8 raised to the 3 divided by 3. So that's the first one, minus, and then we have 4 times 4 squared minus 4 raised to the 3 divided by 3. And you can press enter just to make sure, see, was this typed in correctly? And you can see that it is. We have exactly what I wanted here, and we get the answer 5,017,600. 5,017,600 joules. And that is a lot of energy. So this is a pretty big tank. What's happening is it takes a lot of energy, and you can imagine if it's like electrically powered, this would take up a ton of electricity to do. So just to give you a gauge of why moving water is so expensive, if you were ever curious about that, this is why. Water is basically very heavy, and it takes a lot of energy, a lot of work to move it. Right? But this is the work section. This is probably the, like I said, the hardest problem in the course, at least one of the hardest for sure. Uh, but if you can do this one, I believe that you would be fine with doing any work section, work problem. And with that, I will see you in the next section.